Hello everyone, my name is Han Xiaozhang. I'm very excited to represent our paper, Dense Vision Transformer Compression with Few Samples. This paper is jointly worked with Yifan Zhou and Guohua Wang. Let's start with a brief introduction. Few-shot model compression aims to compress a large model into a more compact one with only a tiny training set, or even without labels. As a form of structured pruning, block-level pruning has recently emerged as a leading technique in achieving high accuracy and low latency in few-shot CNN compression. However, in particular, the issue of sparse compression exists in traditional CNN few-shot methods, which can only produce very few compressed models of different model sizes. Moreover, few-shot compression for vision transformers remains largely unexplored, while the current SOTA methods for VIT compression always falter in few-shot context, which presents a new challenge. In this paper, we propose a novel framework named DCVIT that pioneers few-sample VIT compression. We advocate the benefits and necessity of dense compression in particular applications, which is achieved by selectively eliminating the attention modules while retaining and reusing portions of the MLP modules. To select the blocks with the best recoverability, we propose generating synthetic images as a matrix dataset to address the potential misalignment between the perceived recovery difficulty indicated by the training loss and the actual performance of the fine-tuned models after removing different blocks. Consequently, our method outperforms state-of-the-art few-shot compression methods by a significant margin of 10 percentage points, along with lower latency in the compression of VIT and its variants. As is shown in the figure, the purple dots and dashed line present the specific compression rates achieved by the previous SOTA CNN methods when it is transferred to VIT base, while our DCVIT, which is represented by the rainbow-colored dotted lines, offers much denser compression than other structured pruning methods, which means that for any target compression ratio within a certain range, we can always find one compression setting in DCVIT that is close enough. Moreover, other VIT-based methods were not few-shot, using more than 1 million labeled training images during compression. It's quite a success that our DCVIT uses only less than 0.1% of their training images without labels, but achieves slightly lower or even higher accuracy. The overall framework is illustrated in this figure. Our strategy can be divided into 4 primary stages. In the first stage, we determine the compressed model's network structure based on the target compression ratio. For few-shot learning, removing one entire block leads to a change that can be well approximated by a linear layer. Hence, we propose to replace a dropped block with a small MLP to remedy such errors, which is equivalent to eliminating the attention modules while retaining and reusing portions of the MLP modules. The structure of VIT makes our remedy particularly suitable. Giving a particular target compression ratio, we calculate the minimum number of blocks that should be compressed, denoted as K. We can also calculate the drop ratio of MLP nodes of corresponding blocks, denoted as RK. We change the dimensionality of the intermediate result from 4D to 4D times 1 minus RD, which finalizes the compression structure. In the second stage, once the structure parameters are determined, we operate a block-wise trial procedure to obtain fine-tuned candidate models with different blocks compressed. Following MIR, to fine-tune a candidate model, we use the MSE loss for feature mimicking to minimize the feature gap between the pruned and the original models. In the third stage, we generate a synthetic matrix set to compute recoverability scores of different blocks. Operating under the assumption that a deep neural network can sufficiently train and retain crucial information from a dataset, we propose to utilize the original pre-trained model to generate synthetic images as the matrix set, which is used to reveal the recoverability of removing different blocks. Following Deep Dream, we utilized a batch of Gaussian noise as the initial synthetic images X, giving arbitrary target labels Y. The synthetic images are updated by minimizing the following loss function composed of the cross entropy between the predicted probability and the target label, and the regularization term. As illustrated in the figure, the top one error of candidate models on the test dataset and the matrix loss on the synthetic matrix set are highly correlated. Conversely, the training loss on the tiny training set doesn't show such correlation. We evaluate the recoverability of different blocks on the synthetic dataset and select the blocks with the highest scores. In the final stage, we prune the blocks with the highest recoverability and fine-tune the model progressively using few-shot and unlabeled training set. In the experiment section, we primarily compared our DCVIT method with the SOTA few-shot CNN pruning method practice on VIT base, as well as variants of VIT models, including DIT and swing. Our approach outperforms the baseline by a significant margin. Moreover, we further validate the efficiency of our approach by extending it to CNN architectures and benchmark its performance against several few-shot CNN pruning methods. We use ResNet 34 and MobileNet V2 as the backbone. As shown in this table, our method still outperforms previous methods by a significant margin. Finally, we evaluate the generalizability of our DCVIT. We fine-tune our DCVIT-based model on a collection of commonly used datasets. Compared to the SOTA ConvNets and transformer-based models, the pruned model achieved comparable or even better performance on all the downstream classification tasks, which shows that the efficiency demonstrated on ImageNet can be preserved on the downstream tasks by our few-shot compression method. In this paper, we proposed a novel framework, DCVIT, for few-sample compression on vision transformers, which achieves not only much denser compression options in terms of MACS, but also better performance with higher accuracy and lower latency. However, one common limitation of DCVIT and other few-shot compression methods is that the ratio of compressed MACS cannot be too large. Otherwise, the compressed model's accuracy will drop dramatically. Another limitation is that the few-shot compression is mainly restricted to recognition. However, tasks like detection and segmentation are more intriguing. We plan to test the effect of DCVIT on VIT-based detector compression in future works.